Question number 1C. That will answer many things. State true or false, giving proper justification for each of the following statements. So C is A4 has no subgroup of order 6. A4 has no subgroup of order 6. In fact, this statement is true, and this answers something, that the converse of Lagrange's theorem is not true in general. Because what is A4? A4 is the alternating group of 4 symbols. That means, what is S4? S4 is the group of all permutations of degree 4. S4 contains permutations from the set 1, 2, n to the same set 1, 2, 3 up to n, and each function is a bijection, right? So this is S4, where f is a bijection. What will be order of S4? What is of S4?
24.
24, because order of S4 is nothing but factorial 4, and that is equal to 24. Now we know that out of 24, exactly half is even and half is odd. What is even permutation and odd permutation? If any permutation is given to you, suppose if I give you anything like this, say 1, 2, 3, 4, and say 1 goes to 3, 2 goes to 4, 3 goes to say 3, and 4 goes to 1. So what is this? This is actually a 3 cycle. 1 goes to 3, 1 to 2, I have not mentioned. No. So say 1 goes to 2. Yeah. So 1 goes to 2. So it is actually 1, 2, 4, and 4 goes to 1. So this is a 3 cycle. 3 is fixed by this permutation, so I need not write. But this can be written as 1, 4 into 1, 2. How? Check. 1 goes to 2, 2 goes to 2. So 1 goes to 2, 2 goes to 1, and 1 goes to 4. So 2 goes to 4. 3 goes to 3, 3 goes to 3. So ultimately 3 goes to 3. 4 goes to 4, and here 4 goes to 1. So ultimately 4 goes to 1. So see, this permutation is expressed as product of two cycles. 2 cycles are called transposition. A cycle of length 2 is called a transposition. So given any permutation, I can express it as product of transpositions, not necessarily disjoint. Now, how many transpositions I have expressed this 1 to 4? I express 4 as product of 2 transpositions, and that's why this permutation is a permutation. But if I give you a permutation like this, say 1, 3, 2, 4, this is a 4 cycle in S4. This also belongs to S4. Then I can always express this as 1, 4 into 1, 2 into 1, 3. So this will be a product of 3 transpositions. You verify 1 goes to 3, 3 goes to 3, 3 goes to 3. So 1 goes to 3. 2 goes to 2, 2 goes to 1, 1 goes to 4. So 2 goes to 4. 3 goes to 1, 1 goes to 2, 2 goes to 2. So 3 goes to 2. And 4 goes to 4, 4 goes to 4, 4 goes to 1, so 4 goes to 1. Now this particular permutation is expressed as product of 3 transpositions. So this is an odd permutation. So whatever permutation group, symmetry group is given to you, if it is Sn, you know that order of Sn is factorial n. But always there exist factorial n by 2 numbers of even permutation and exactly same number of odd permutations. Okay. Now the set of all even permutations in Sn form a group, and that group is called alternating group and denoted by An. So what is in particular, what is A4? A4 is the permutation group of all even permutations of degree 4. Right? So order of A4 is factorial 4 by 2, that is 12. Now the statement says that A4 has no subgroup of order 6. 6 divides 12, but there does not exist any permutation, means any subgroup of A4 of order 6. That I have to prove. Once it is proved, it will work as a counterexample to show that the converse of Lagrange's theorem for finite groups is false. That is true in case of finite abelian groups, but in case of non-abelian groups, that is not the case. Okay. Before proving this, we need to know a result that is important, and that result says if H and K are finite subgroups of a group B, then say we do not know whether HK is a subgroup or not. We know that HK is a subgroup if and only HK equal to KH, but we don't know whether HK equal to KH or not. But if they are finite subgroups of a group G, then the cardinality of HK, I'm still, as I said, it has cardinality. The cardinality of HK, not claiming it, will be equal to order of H into K divided by order of H intersection K. So this is a formula for finding the cardinality of HK. So let us prove it. Proof. Okay. Let say D equal to H intersection K. Then you know that H intersection K is a subgroup of G. Then D is a subgroup of G, because intersection of any number of subgroup is a subgroup. Also, D is contained in K and K is a subgroup of G. So therefore, D is a subgroup of K, right? Because ultimately D is a group and K is also a group. D is contained in K, so D has to be a subgroup of K. Since D is a subgroup of K, you can always express your K as union of cosets of D in K. Okay. Thus, I can always express K equal to union, say I goes from 1 to T, D Ki, where Ki belong to K. What are these DKI? These DKI are distinct right cosets of D in K. Right? Okay, since cosets are equivalence classes, so definitely the main group is expressible as union of all equivalence classes. We know in the proof of Lagrange's theorem, we know that to okay, I lost network, so let me share. Right. So what is K? We have seen K is nothing but union I goes from 1 to T, DKI. This. And what else we know? We know that D is contained in H. Why so? The reason is, see, D is equal to H intersection K. So definitely D is a subset of K. If D is a subset of K, what happened to HD? HD definitely equal to H. Do you follow this? The reason is, you see, H is always a subset of HD. There is no doubt. Why there is no doubt? Because H belongs to H can be expressed as H equal to HE, where E is the identity element in D. Since D is a group, it is a subgroup, so it is a group. Identity element is inside. So I can say this HE is inside HD. So this proves that H is a subset of HD. But how can you prove that HD is a subset of H? Choose any element HD, say X belongs to HD. This implies there exists some H in capital H and D in capital D, such that X is equal to H into D. That is the definition of HD. But to know that D is contained in H, so this D is also an element of H. This is contained in H. And product of two elements of H is again in H. So this belongs to H. and so HD is contained in H. So they are same, right? So we have proved that HD and H are same. If they are same, then what is HK? HK is union I goes from 1 to T, HD KI is equal to union I goes from 1 to T, HD is H, so it is HKI. Okay. Now, whether all these cosets HK1, HK2, ultimately HKT are they distinct? Let us see. If say I not equal to J belong to the set 1 to 3 up to T, and suppose the corresponding cosets HKI is equal to HKJ. I want to prove that all these cosets are distinct. Suppose they are not distinct. They are not distinct means suppose there exist I and J in the set 1, 2, 3, 4 up to T, such that I is not equal to J but HKI equal to HKJ. I show that this is not possible. If HKI equal to HKJ, it means you know that when two right cosets are equal, it means KI KJ inverse belongs to H. This is the definition of equality of cosets. But initially, KI KJ are taken from K, and K is a subgroup. Also, KI KJ inverse belongs to K because K is a subgroup of G. The reason is since K is a subgroup of G, therefore KI KJ inverse belongs to K intersection H, and K intersection H is D. And if you say KI KJ inverse belongs to D, so again by using the equality of right cosets, DKI is equal to DKJ. But is it possible? Answer is no, because you have said that the index of D in K is T, exactly T. So all these right cosets DK1, DK2, DKT are distinct. So this is a contradiction. If I is not equal to J, DKI cannot be equal to DKJ. So therefore, HK1, HK2, ultimately HKT are distinct right cosets, okay, of H. Fine. Therefore, what will be cardinality of HK? Cardinality of HK, you see, HK is equal to union of all such HKIs. And this HK1, HK2, HK all are distinct. Two cosets are distinct if and only if they are disjoint. You know, two cosets, if they have one element in common, then they should be identical because they are equivalent classes. So that means what will be the cardinality of HK? It will be sum of the cardinalities of each of the cosets. So cardinality of HK is summation I goes from 1 to T, cardinality of HKI. Okay, but you know that cardinality of HKI is same as order of H. We have seen it in case of Lagrange's theorem. So it is summation I goes from 1 to T. It is exactly equal to cardinality of H, means order of H. So total T number of order of H. So T times order of H. But what is T? T is, you see, index of D in K. That is order of K by order of D. This is by Lagrange's theorem. By Lagrange's theorem. So we have proved that this is equal to order of K divided by order of D into order of H. This is equal to order of H into order of K divided by order of D. Order of D means order of H intersection K. So this is the formula for the cardinality of HK if H and K are finite subsets of G. Is it clear? Anything to be explained? Do you require any explanation in this proof? Anyway, I'll send you, or you have the video. Okay, this is not recorded. So I'll send you the material, whatever we are writing. So there you can check whether you have understood or not. We have not used anything that is not known to you. Whatever we have done so far, we have used only that. Basically, Lagrange's theorem. Anyway, so this result is now at our hand. With the help of this result, we'll argue that A4 cannot have a subgroup of order 6. Let us see. So we'll prove it by the method of contradiction. So this is our main argument. So justification. So if possible, let A4 have a subgroup of order 6. Let us say the subgroup is H. Fine. Now tell me the number of cycles of length 3 in S4 is equal to. I want to find out the exact number of 3 cycles in the group S4. How to find it? Let us see this first. Let us not be too ambitious. First of all, let us try to find out exact number of cycles of length 3 in S3, because S3 is very much known to us. S3 is a known group for us. We know that S3 contains identity permutation, then 1, 2, then 1, 3, then 2, 3. These are 2 cycles, and 2, 3 cycles, 1, 2, 3, 1, 3, 2. So since this group contains only 6 elements, we can enlist elements very easily. So we can count that how many 3 cycles and how many 2 cycles are there. But even if we do not, or we cannot enlist them so easily, still we can say that how many 3 cycles will be there. Remember, not only 3 cycles, any cycle of length R. The reason is, you see, suppose you are working with Sn. If you are working with Sn, let us try to find out the number of cycles of length 3. So a cycle of length 3 is always of this form, ABC. Listen to me carefully. This is very important. Any 3 cycle in Sn is of this form, ABC, where ABC, these 3 elements come from the set 1, 2, 3, 4 up to n. Right? In how many ways A can be chosen? Anybody?
N.
N. Your name, please?
Joshri.
Okay. So Joshri said that the first element A can be chosen in n ways. So n times. Once the first element is chosen, in how many ways B can be chosen?
N-1.
N minus 1. Correct? And you know that once A and B both are chosen, C can be chosen in n minus 2 ways. But tell me, I have written this 3 cycle as ABC. Is it same as BCA? Whether these 2 cycles are same or they are different?
Same.
Same. Because the image of A is B, image of B is C, image of C is A. Here also, image of B is C, image of C is A, and image of A is B. So they are basically same. If someone writes CAB, then also same. So that means the same 3 cycle can be written in 3 distinct ways. So our total number of distinct 3 cycles will be n into n minus 1 into n minus 2 divided by 3, right? Do you follow this? The total number of 3 cycles in Sn will be n into n minus 1 into n minus 2, because you have to choose 3 elements from n elements. First element can be chosen in n ways. Second element can be chosen in n minus 1 ways, because your first and second element cannot be same. And the third element can be chosen in n minus 2 ways, because you know that no 2 elements can be same. But the same combination can be written in 3 different ways. And all these 3 different representation will give you the same element. So that's why the total number should be divided by 3 to get the exact number of distinct 3 cycles. Is this clear? So n into n minus 1 into n minus 2, this is the exact number of 3 cycles. Now I can further, of course, this is fine for me, but still, you see, this can be written as n into n minus 1 into n minus 2 into, the next one will be n minus 3 dot dot, let us go up to 1, and here 3 into n minus 3 into dot dot, let us go up to 1. So what is this? This is actually factorial n divided by 3 into factorial n minus 3. So this is the formula for finding exact number of 3 cycles in Sn. Now there is nothing special about 3. So this 3 can be replaced by any R. So in general, in the permutation group Sn, the number of distinct R cycle where R is less than equal to n is factorial n divided by R into n minus R. Okay, so this is the formula. Now let us come back to our case. What will be the number of cycle of length 3 in S4? Quick, now you know how to calculate. the number of cycles of length 3 in S4. You have 4 elements. You have to choose 3 elements. And every particular 3 cycle has 3 different representations. So how many total?
8.
8. Very good. Your name?
Devashri.
Okay, very good. So Devashri said, see, the first element can be chosen in 4 ways. Second element can be chosen in 3 ways. Third element can be chosen in 2 ways, and each has 3 different representations. So total number is 8. Very nice. So that means in S4 we have 8 3 cycles. Now every cycle of length 3 in S4 is even or odd? Any 3 cycle is even permutation or odd permutation?
Odd permutation.
Even or odd? Who said odd?
Suhail.
What's your name?
Suhail.
Sorry, Shwel. Okay, so Shwel said that every 3 permutation is odd. See, let us take any 3 cycle, say 1, 2, 3. Just a few minutes ago, I have expressed this as product of transpositions like this, 1, 3 into 1, 2. Right? Okay, what do you mean by even permutation or odd permutation? Every permutation can be expressed as product of transpositions. This is the first thing. After expressing a permutation into product of transpositions, you check the number of transpositions. If the number of transposition is even, then the permutation is called an even permutation. If the number is odd, then the permutation is called an odd permutation. Every 3 cycle can be expressed as product of 2 transpositions. Is this clear? So therefore, every 3 cycle is an even permutation. Actually, how to count? The simplest thing to remember is, if you are given a cycle of length r, the total number of transposition by which you can express this will be r plus 1. So if r is odd, your permutation has to be even, and if r is even, your permutation has to be odd. So every 3 cycle is basically an even permutation. So every cycle of length 3 in S4 is an even permutation. Even permutation. And so is in A4, correct? Because A4 is the normal subgroup of S4 containing all even permutations. Since we have assumed that order of H is equal to 6, remember, we have assumed that A4 has a subgroup H of order 6. Since H contains 6 elements, you have 8 3 cycles in your group A4, then at least 1 3 cycle should be outside of H. Do you follow this? Do you follow what I said? I said that your A4 contains a subgroup capital H of order 6. That means H contains 6 elements. How many 3 cycles are there in A4? 8. So can all 3 cycles be contained in H?
No.
No. Very nice. This is a simple observation. H contains 6 elements. There are 8 3 cycles. So at least 1, actually 2, or maybe more than 2, but at least 1 3 cycle will be outside of H. So there exists a cycle of length 3, say sigma. This belongs to A4, but not in H. This is clear? Fine. Suppose sigma square belongs to H. We'll check that whether sigma square belongs to H or not. Suppose sigma square belongs to H. If sigma square belongs to H, then sigma square into sigma square belongs to H. Why? If sigma square belongs to H, then sigma square into H is a subgroup. Yeah, correct. So since H is a subgroup, it is a group. So product of 2 elements is again inside this group. Fine. That means we are saying that sigma to the power 4 belongs to H. But observe something. You have a 3 cycle. Your sigma is actually a 3 cycle A, B, C. So what happened to sigma square? Sigma square is ABC into ABC. Calculate. A goes to B, B goes to C. So A will go to C. B goes to C, C goes to A. So B will go to A. And C goes to A. And A goes to C. So, sorry, something missing. A goes to B, B goes to C. So A goes to C, B goes to C, C goes to A, so B goes to A. And C goes to A goes to B, so C goes to B. That's fine. So this is my sigma square. What will be sigma cube? Sigma cube is sigma square into sigma. A goes to B and B goes to A. So A goes to A. B goes to C. C goes to B. So B goes to B. C goes to A and A goes to C. So C goes to C. So that means your sigma cube is nothing but the identity permutation. And remember, this is a fact that the order of a cycle is exactly equal to its length. Whatever be the length of a cycle, that is exactly the order of that particular element in the group. So that means order of sigma is 3. If sigma cube is identity, what is sigma to the power 4? It is same as sigma. So if you say your sigma to the power 4 belongs to H, this means sigma belongs to H. But is it true? No, this is a contradiction because you have assumed sigma is outside H. So it proves that sigma square is also outside of H. Fine. Let K be a subgroup of A4, which is generated by the element sigma. So what are the elements inside K? This is a cyclic subgroup. What are the elements? Sigma is the generator. Sigma will be there. Sigma square will be there. Sigma cube will be there, but sigma cube is identity. So these are the 3 elements: sigma, sigma square, and identity. Then what will be order of this subgroup K? This will be 3. Okay. Therefore, just now we have seen that cardinality of HK is equal to cardinality of H into cardinality of K divided by cardinality of H intersection K, means order, because these are groups. What is order of H? Order of H is 6. What is order of K? 3. What is order of H intersection K? Can anybody tell me that what is order of H intersection K?
Identity.
Okay. Yeah, means what will be the order?
1.
1. You are? There was in Jayasri. Very good. So what Jayasri said is exactly correct, because you see that K contains sigma, sigma square, and identity. So it means sigma is not there in H, sigma square is not there in H. So what is the only possibility? The only possibility is that the identity is definitely there in H because H is a subgroup. So identity is the only common element. So that means order of H intersection K is 1. So it is 18. Is it possible that order of HK means cardinality of HK is 18? Certainly not, because HK is a subset of A4. H and K both are subgroups of A4. So HK is a subset of A4. A subset cannot have more element than the superset. This is a contradiction. Why? As HK is contained in A4 and order of A4 is 12. So that means we have proved, therefore our supposition was wrong. A4 has no subgroup of order 6. So this is done. Okay, this is an important example. Let us see question number 1b. Question number 1b. So the statement is the groups S4 and Z24 are isomorphic. Tell me, true or false?
False.
False. Why?
Z24 is cyclic and S4 is not cyclic.
Yeah, very good. So this is very good explanation. You see, even if you do not want to say cyclic, then also we can argue, because Z24 is abelian and S4 is non-abelian. So a group which is abelian and the another group which is non-abelian cannot be isomorphic. Even homomorphic image of an abelian group is abelian. So there is no question about isomorphism. So this is false. The reason is, this is definitely false, because S4 is not abelian, whereas Z24 is abelian. So similarly, if somebody asks you that what about Klein's 4 group and Z4, whether they are isomorphic, the answer will be no, because then your logic will be helpful that this is, since both groups are abelian, so by arguing like this that they are abelian, we cannot conclude. But here that cyclic property will be used. This is not cyclic and this Z4 is cyclic. So they are also not isomorphic. Not isomorphic. There is another problem in your problem set. You will find that show that this group Z plus is not isomorphic to R plus. What is the reason?
Z plus is cyclic, R plus is not.
How do you know R plus is not cyclic?
We have this rational number which
Yeah.
cannot express as.
Okay, fine. We know that the additive group of rational number is not cyclic. Then how will you argue?
If we suppose that R plus is cyclic, then R should be R can be expressed as n R, where n is a.
No, that is fine. You can argue like that. But even I think simpler argument is there. Every subgroup of a cyclic group is cyclic.
Yeah.
So if R plus is cyclic, Q plus will also be cyclic. That is false.
Yeah.
So that means R plus is not cyclic, Z plus is cyclic. So they cannot be isomorphic. Again, the same reason that this is not cyclic and this is cyclic. Now, if I ask you that what about, say, Q plus and R plus, are they isomorphic? Anybody? Now, both are not cyclic. So this argument will not work. Are they isomorphic? Anybody? What is an isomorphism?
An isomorphism is a function from G to G dash, where F is 1, 1 and on 2, and also homomorphism.
Homomorphism, very good. Who are you speaking?
So Jayashree.
Jayashree. Okay, so fine. So Jayashree, you know the definition. Everybody knows, fine. But you have said that F has to be a homomorphism, along with it has to be a bijection. Can you define a bijection from Q to R?
No, sir. Q is countable.
Very good. So here analysis saves us. Here see, without knowing that group theoretic argument, simply by analysis we can argue. Because in analysis we have learned that Q is countable, R is uncountable. So there does not exist any bijection from Q to R. So forget about isomorphism. Simple bijection cannot be defined. So they are not isomorphic. So they are not isomorphic. The reason is this Q is countable and R is uncountable. In fact, there is no analysis, simply set theory. This is uncountable, this is countable. So they cannot be isomorphic. Now, what about R plus and R star dot? R star dot means this R star means R minus singleton 0. Are they isomorphic? Now both are uncountable. So this argument will not work. Now again we have to take care of group theoretic argument. In case of isomorphism, what have we learned? We have learned that if F is an isomorphism from a group G to G prime, if this is an isomorphism, then if A belongs to G of order n, then what is order of Fa? Can anyone tell me?
N.
N, right. That means order of every element of finite order, the isomorphic image of that element will also have the same order. Very good. Now, the question is, what is order of 1? Not 1, say minus 1. Minus 1 belongs to this R star dot. What is order of minus 1 in R star?
2.
2. Very good. Minus 1 square is equal to 2. How many elements are there in R star of order 2? Other than minus 1, do you have any other element whose order is 2?
1.
No, 1 has order 1 because 1 is 1. 1 is the identity, no?
No.
Isn't it? Yeah, no other. That means there exists exactly one element here of order 2. If this group R star dot is isomorphic to R plus, then inside R plus also we must have an element of order 2. Does this group possess an element of order 2? Inside R plus, can you find any real number x such that x plus x is equal to 0?
No, sir.
No. Other than 0, there does not exist any element. And 0 order is 1 because that is the identity. So that means there does not exist any non-identity element in R plus having order 2. So these two groups cannot be isomorphic. So these two groups are also not isomorphic. Why? The reason is R star dot contains an element of order 2, but R plus does not have any such element. That's all. What about R star dot and C star dot? Now you should argue. You know now. The same logic will be applicable. Can you complete the statement? They are also not isomorphic. Why? Anybody? Why C star is not isomorphic to R star? See, inside C star, you have an element I. What is order of I?
4.
4. Do you have any element in R star having order 4?
No, sir.
No. Here, for all x belong to R star, order of x is not equal to 4. So they cannot be isomorphic. So they are also not isomorphic. So these are some examples. These are not very difficult but tricky. And in competitive exams, this type of questions are asked, that whether these two groups are isomorphic or not. So if you know the reasons, you can easily answer. Anyway, let us solve another problem. Say question number 17. F from G to H be a group homomorphism with kernel F is equal to K. For A belongs to G, show that Ka is this set. Okay, so what is given? Question number 17. Let F from G to H be a homomorphism let A belong to G, and what else? Kernel F is equal to K. Then show that the right coset Ka is precisely the set of all G in G for which Fg is equal to Fa. Yeah, this is to be shown. So we have to prove two sets are equal. That means we have to show that this right coset Ka is contained in this set and this set is also contained in Ka. So solution. Take any element from the right coset. Suppose x belongs to Ka. This implies there exists some K belongs to capital K such that x is equal to Ka. I have to prove that f of x is equal to f of A. This implies f of x is equal to f of Ka, but f is a homomorphism, so it is f of k into f of A. What is f of k? K belongs to capital K. Capital K is the kernel of f. So what is f of k?
Identity.
Identity in H. So this is identity in H. Let me denote it by this way. Into f of A, where is the identity in H. And who has told me the answer? Your name, please.
Sohail Ahmed.
Sohail Ahmed. Okay, very good. This is equal to f of a. So since f of x is equal to f of a, it proves that x belongs to this set all g in G such that f of g is equal to f of a. So therefore, the right coset Ka is contained in the set of all g in G such that f of g is equal to f of a. Fine. We have to prove that the set in the right hand side is also a subset of this left hand side. So let G belong to G be such that f of g is equal to f of a. I have to prove G belongs to Ka. If f of g is equal to f of a, then f of g into f of a inverse, this is equal to identity element in H, because fg and fa both are elements of H. So if I multiply both sides on the right hand side by fa inverse, we'll get this equation. But f is a homomorphism, so this is fg into f of a inverse, the property of homomorphism. This implies your f of ga inverse is equal to H, and both these two things are true since f is a homomorphism. So we should always mention that why it is true. If f image of this element ga inverse is identity, this means ga inverse must belong to the kernel of f, that is k. And if ga inverse belongs to k, ga inverse into a, this must belong to the coset ka. This implies ga inverse a is equal to g, this belongs to ka. So it proves, therefore, the set of all g in G such that f of g is equal to f of a, this set is contained in Ka. So hence they are same. Ka is same as the set of all g such that fg is equal to f. Right? This is that. Let us see another kind of problem that is not there in your problem set, but let me show you. Show that there exist at most 6 homomorphism from S3 to Z6. S3 is the symmetric group having 6 elements. Z6 is the cyclic group having 6 elements. We have to show that we cannot find more than 6 homomorphisms from S3 to Z6. How? To answer this question, first of all, we have to see the nature of S3 carefully. What do I mean? I can always write S3 in this way. It is a group which is generated by 2 elements, 1, 2 and 1, 2, 3, with the property that 1, 2 into 1, 2, 3, or forget about this. If I do not write anything, then also this is true. I am claiming that S3 is actually generated by 2 elements, 1, 2 and 1, 2, 3. What do you mean by generated by 2 elements? Generated by 1 element is simple. In case of cyclic group, it happens. So if you have a cyclic group, say G is equal to a group generated by some element X, what is the meaning? Meaning is for every G in capital G, there exists a natural number or integer, say, such that G is equal to X to the power n. If I say that no, it is not a cyclic group, but it is generated by 2 elements XY, what is the meaning? Meaning is for every G in G, there exists an integer n and another integer m, such that this G is actually product of xn and yn. So if G is expressible in this way, then we say that G is generated by these 2 elements. Similarly for 3 elements, 4 elements, etc. So if I claim that S3 is generated by 1, 2 and 1, 2, 3, So I have to verify that every element in S3 can be expressed as product of some power of 1, 2 and some power of 1, 2, 3. Let us verify. Your S3 contains 6 elements. S3 contains identity permutation, 2 cycle 1, 2, 2 cycle 2, 3, 2 cycle 1, 3, 3 cycles 1, 2, 3, and 1, 3, 2. Now verify, take identity. How can you express identity as some power of this 2? Yes, I can. Simply, I can write identity is equal to 1, 2 square into 1, 2, 3 cube. Done. 1, 2 square is identity. 1, 2, 3 cube is also identity. So identity is equal to identity into identity. Why 1, 2 square is identity? Because a few minutes before I said that order of a cycle is exactly equal to its length. How can you express 1, 2? I can express 1, 2 as 1, 2 to the power 1 and 1, 2, 3 to the power 3. That's all. Because this will be identity, this will be 1, 2. How can you express 2, 3? 2, 3 is nothing but 1, 2 into 1, 2, 3. Check. 1 goes to 2. 2 goes to 1. So 1 goes to 1. 2 goes to 3. 3 goes to 3. So 2 goes to 3. 3 goes to 1. 1 goes to 2. So 3 goes to 2. So you verify. Similarly, 1, 3. How 1, 3 will be expressed? Most probably 1, 3 will be 1, 2 into 1, 2, 3 square. Let me check. 1, 2 into 1, 3, 2. 1 goes to 3 and 3 goes to 3. So 1 goes to 3. 2 goes to 1. 1 goes to 2. So 2 goes to 2. And what else? 3 goes to 2. 2 goes to 1. So 3 goes to 1. Right. And how 1, 2, 3? 1, 2, 3 can be expressed as 1, 2 square into 1, 2, 3 to the power 1. And 1, 3, 2 can be expressed as 1, 2 square into 1, 2, 3 square. So see, every element in S3 is actually expressible in the form x to the power n into x to the power m, where x is equal to 1, 2 and y is equal to 1, 2, 3. So this group S3 is expressible with the help of 2 elements only. Very nice. Now let us come to our problem. Let F from S3 to Z6 be a homomorphism. Okay, this implies f of the element 1, 2, comma, f of the element 1, 2, 3, both should belong to Z6, right? What will be order of f of 1, 2? Anybody? Can anyone tell me that what are the possible orders of f of 1, 2?
2.
Why not 1? This is not isomorphism, this is homomorphism. In case of homomorphism, we know that if f is a homomorphism from a group G to G prime, and if A is an element in G such that order of A is n, then always order of f of A divides order of A. Okay. So order of f of 1, 2 is either 1 or 2. What about f of 1, 2, 3? It will be either 1 or 3. But you see, these two are elements of Z6, and we know that every element in a group, in a finite group, divides the order of the group. So this implies, order of f of 1, 2, this divides 6, and order of f of 1, 2, 3 divides 6. Also, order of f of 1, 2, 6 means order of Z6. This should divide order of 1, 2, that is equal to 2, and order of f of 1, 2, 3, this should divide order of 1, 2, 3, that is equal to 3. So combining both these two cases, what are the means? We can say order of f of 1, 2 is equal to 1 or 2, and order of f of 1, 2, 3 is equal to 1 or 3. Okay. Now you tell me, is it enough to know f image of 1, 2 and F image of 1 to 3 to know every element of Z6? I think my question is not clear. My question is, I know two things now, that order of F image of 1, 2 is either 1 or 2, and order of F image of 1 to 3 is either 1 or 3. So basically, I have information regarding these two elements, this element and this element. If somebody tells me that, okay, this element is this particular element in Z6 and this element is this particular element in Z6, is it enough to know every element in Z6? Means not in Z6, but the homomorphic image of S3. I'm talking about this. I'm talking about F is from S3 to Z6. So if you know regarding these two elements, is it enough to know everything about F of S3? Answer is yes. Because if you give me any element here, if you give me say any y belong to F of S3, then that means there is some x in S3 such that F of x is equal to y. But x belongs to S3 means x is expressible as product of powers of 1, 2 and 1 to 3. So definitely this x is of the form 1 to 3 to the power I, 1 2 to the power j, and 1 2 3 to the power I. So my f of x will be f of 1 2 to the power j into 1 2 3 to the power I. F is a homomorphism, so this will be simply f of 1 2 to the power j into f of 1 2 3 to the power I. So if I know this element and this element, then I know this element, and this element is y. Now the only thing is that what are the possibilities of this element? How many elements are there in Z6 with order 1 or 2? Can anyone tell me? How many elements are there in Z6 with order 1 or 2? 1, okay, fine. Z6 is the set which contains elements 0, 1, 2, 3, 4, 5. These are the 6 elements. These are equivalence classes. 0 has order 1, that I know, that is fine. Tell me how many elements are there of order 2?
3 only.
Yeah, so there exists only one element of order 2. So that means, therefore, your F image of 1, 2 is either 0 or 3. Two choices only, right? Because order of this is either 1. If order of this element is 1, it should be 0. And if order of this element is 2, then it has to be 3. Similarly, what is the possibility of f of 1 to 3? Either its order is 1 or 3. If order of this element is 1, it has to be 0. How many elements are there in Z6 of order 3?
2.
Sure?
I mean the number 2. I mean 0. Element 2.
Yeah. 2. 2 has order 3. Any other element of order 3?
5. No. 4.
What? 4, correct. So it has two more possibilities. That f of 1, 2, 3 is 4, 8. So your f of 1, 2 can be chosen in 2 ways. F of 1, 2, 3 can be chosen in 3 ways. So in how? Yeah. Oh, sorry. 2 and 4. 4, 4, 2. So therefore, f can be chosen in at most. I am not saying that in every case you will get a homomorphism, but these are the maximum possible choices. That is what we are asked to find out. So at most 2 into 3, that is 6 ways. So this is the solution. I will stop now. So you have 10 minutes to ask me anything that you have not understood. I will try to answer if possible, from today's class or from the lectures, or if you have anything else in algebra. So I'll be on.
Last part,
please.
last problem.
Last problem, that at most 6 homomorphisms. Last part. Have you understood this, that if I know f of 1, 2 and f of 1, 2, 3, it is enough for me to find out all homomorphisms? Means it is enough for me to define the homomorphism. Have you understood this? My question is, this is the main point, that f is a homomorphism from S3 to Z6. S3 is generated by two elements, 1, 2 and 1, 2, 3. So if by any means I know f image of 1, 2 and f image of 1, 2, 3, is it enough for me to define f? That is my question. Have you understood this?
No, sir.
Okay. Let me tell you why it is enough. Suppose somebody by some means told me that yes, I know that f of 1, 2 is say 3 and f of 1, 2, 3 is say 2. Suppose this information is provided. I want to define f completely. That means I want to define what is f of x. This formula I want to define. What do? I will pick any element x from S3. I know that S3 is generated by two elements, 1, 2 and 1, 2, 3. This I know. So if x belongs to S3, there exists integers m and n such that your x is equal to 1, 2 to the power n into 1, 2, 3 to the power m. This will imply f of x is equal to f of 1, 2 to the power n, 1, 2, 3 to the power m is equal to, f is a homomorphism. Ultimately, it is f of 1, 2 whole to the power n. Whole to the power n means now you are in Z6, remember. So whole to the power n means f of 1, 2 addition modulo 6, f of 1, 2 this way n times plus f of 1, 2, 3, this will be addition modulo 6. And this is not power, this is actually multiple. Right? Understood?
Yes, sir.
So, but you know the values of f of 1, 2 and f of 1, 2, 3. You know that f of 1, 2 is 3. So you have 3 addition modulo 6, addition modulo 3, addition modulo 6. How many times? N times. Plus m times you have 2, 2, 2 and so on. M times you will have 2. Now you count, you will get the value of x. So whatever x you give me, I can produce its value under f, its image under f, because I know f of 1, 2 and f of 1, 2, 3. So the main issue is to find f of 1, 2 and f of 1, 2, 3. The number of ways I can choose f of 1, 2 and f of 1, 2, 3. The number of ways I can choose homomorphisms from S3 to Z6. So the main issue is to choose f of 1, 2 and f of 1, 2, 3. And that we have shown that there are at most 6 ways by which we can choose. Is it okay now?
Yes, sir.
Okay. Anything else? So in this tutorial regarding conjugacy, etc., we could not discuss. So our syllabus for algebra will be completely unit 1, not anything in unit 2. So the first 15 lectures in unit 1, that will be the syllabus for algebra 1, that is 101. And 102 syllabus I told you yesterday that the unit 1 plus 3 lectures in unit 2. So still 3 minutes. If you have any doubt, please ask me.
Sir,
Yeah, please.
in the last problem, we can choose any generator of the group.
Yeah. First of all, S3 is given, so you pick generators.
Any group, in case when other groups also.
Yeah, if other groups are there and if you know they are generators, you can do it. Suppose if you are given a cyclic group, then it is very easy because cyclic group will have only one generator. Find out all homomorphisms from say Z4 to Z6. That is easier because you know that Z4 has only one generator. Means maybe Suppose somebody suppose pull it through. How to find f of 1? Order of f of 1 will divide order of 1 first of all. And second thing, since f of 1 is there in the codomain group, that is Z6. So order of f of 1 will divide the order of the codomain group, that is order of Z6. So order of 1 will divide 4 as well as 6. So what are the natural numbers which divide 4 as well as 6? 1 and 2. So either order of f of 1 is 1 or order of f of 1 is 2. So either it is identity or it is 2. So there are two possibilities only. Is this clear?
Yes, sir.
Yeah. Okay, so let me stop. It is 5:31. So before exams, we'll not have any tutorials. So I'll declare the dates. Let this exam be over next week. So you have exams on 19th and 20th, no? Am I right? 19 and 20 or 25?
Yes, sir.
I forgot. Okay, 19 and 20. Nice. So I'll inform about timing, etc. Exact timing on 18th. And enough time and enough options will be given. So don't worry. Please study the things, whatever discussed. It will be open book, but you have to do. If you do not understand, you cannot write. So please try to understand. If you have doubts, you post it in the group or you discuss among yourself. You ask me. We'll try to settle the issues. So thank you. Wish you all the best
Sir?
for the exam. Yeah.
Thank you. Sir, how do we have to submit the answers?
You have to make the PDF file, single PDF file, and send it to my email ID. That from that email I am operating, sudharhkd@gmail.com.
Okay, sir.
So I'll write it on the instructions. I'll write on the WhatsApp or I'll mail you also. Okay, thank you.
Thank you, sir.
Thank you, sir.